Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover spring mass systems, in particular, free undamped motion. So this is like the beginning of what you start talking about, like pulling down a spring and watching the thing bounce back and forth. And what undamped motion means is that the spring is going to bounce back and forth indefinitely. Now, like in a real system on that we tend to work with, it tends to slow down, and that's called damped motion, and we'll get there. But we have to start out with the most base case, which is going to be this undamped motion, which really just looks like a sine wave that goes back and forth as your spring basically bounces up and down. So Hooke's law says the amount of stretch of a spring depends on the mass attached to it, which makes sense. The heavier the mass, if you put it on a spring, it's going to pull this thing down. So really what we have here is, let me make sure, I'm going to have some kind of spring that looks like this. Nice spring, I know. Now at the end of the spring, what we're going to do is we're going to put a mass on here, so some kind of block is going to go right here. So this is going to be our mass, which really is we're going to call this F, because it's going to be the force of our mass. And really, the bigger the mass, the bigger the elongation of the string, so, or the spring. So if I have, the exact same spring, if I have a smaller force on it, it's not going to stretch as much. So that's really what the second part says. Therefore, the spring exerts a restoring force, F, opposite to the direction of elongation and is proportional to the amount of elongation. So really, Hooke's law comes down to this formula, that the restoring force, S, is equal to the spring constant times this, this elongation. So, as this pulls the spring down, the spring, of course, is going to pull it back up at the same time, because if this mass is not moving, we know it's not. We know it's at what we call equilibrium. So, the amount of stuff pulling down has to be equal to the amount of stuff pulling up, or it would be moving. So, let's do an example. We're going to, go after Hooke's law. I'm going to give you two of the three things, and we're going to find the third one. So in this case, this is given a spring that stretches half a foot from a 10-pound weight, determine the spring constant. Okay, so what I know is we have this this equation, F is equal to K times S. Now, the spring pulls opposite or equal opposite to the force of this weight, so that means this 10 is going to be equal to K, which we're not actually sure because K is our spring constant, and then we know that S is our elongation, so this is going to be times half of a foot. So if we're using pounds, this has to be in feet. So if this said 6 inches, you'd have to turn this into feet, because our forces and stuff have to have the exact same units. So you'll notice me do that in upcoming examples. Okay, so what this implies is that this means that multiplying both sides by 2, 20 is going to be equal to this spring constant. Now let's do kind of like a part B to this. So let's say it's the exact same spring. Could I figure out how far the spring would elongate if I do a different weight? So, let's say same spring. So, what would the elongation be for an 8-pound weight? So remember, we're talking about the same spring. What I mean by the same spring is that we have the same spring constant. Every spring has its own spring constant. You can kind of think of it this way: like you see, like a really massive, thick spring, it's going to be harder to squish or elongate. So therefore, it's going to have a different spring constant than maybe a really thin spring. Now, So if you know the elongation of any particular spring through some particular force, then you can find its spring constant, which is what we did here. Therefore, if I put on a different force or different weight, we can actually figure out the elongation of that. So if you're thinking about like for instance, if you're putting like a spring on a car, I need to know, is it going to hold this particular weight of, say, like a car or a truck over, different forces. So that's why it's nice to know the spring constants. So then you're putting on the correct spring for the, for your correct application. All right, so in this case, we still have F is equal to K times S. So F is equal to K times S, except K we know is equal to 20 because we're talking about that exact same spring. Now, our weight is going to be equal to 8 pounds now, so 8 is equal to 20S. Therefore, 8 over 20 is equal to S, and they are both divisible by 4, so this is going to be equal to 4/5 feet. So that's how far it's going to go. All right, now we're going to use Newton's second law to talk about, what happens if I take this mass and I pull it down and then I let it go. So what's going to happen if you pull this mass down and you let it go, it's going to, the restoring force is going to shoot it back up. And then, the mass eventually is going to pull it back down, and the restoring force is going to shoot it back up. So what you're going to see is you're going to see this spring bounce back and forth. So let's talk about that, which comes down to Newton's second law. Newton's second law says, what's going to happen to the spring if, we have this unstretched spring that's basically sitting here, and once we put a weight on it, it's going to apply, the force for this weight. So let's call this, the mass right here, which applies that weight, and it's going to pull that string down, that spring down, and it's just going to basically sit here. So I just put that mass on here, applies this weight or this force, and it's just going to sit here at equilibrium. Now, what happens if I take this mass, or I take this weight and I pull it down a little bit here, and then let's say I just let it go? Well, at equilibrium, it just sits here and it doesn't move. But if you pull it down, what's going to happen is this spring is going to, it's going to pull it back up, proportional to its its new stretch, which is going to be equal to this S, and then also this extra X that I pulled it down at. Remember that right now the spring is already pulling this thing back up at the same time that this mass is putting this weight on it straight down. So it does already have a equal and opposite force, which is that Newton's second law. So this is what's going to happen when I pull this thing down, this extra X. Now it's going to have a restoring force of that spring constant times, remember this initial pullback from this S, and then this extra pullback from this X. So let's kind of go through the math here. So what I know is that the weight that this mass applies to the spring, the weight is going to be equal to, its force, which is going to be mass times acceleration, and the acceleration is, due to gravity, which is we call just G. So, this really is the same thing as that force right there, M times acceleration. And so that's what we said. Weight is equal to mass times the acceleration due to gravity, which is why it's a force. Now, the Hooke's law says that, that force is equal and opposite to this, it's equal to this spring constant times the elongation, which is what we just practiced doing a second ago, finding K and then eventually also finding S. So if I have two of these things, I can find the third one. Now, we know this spring is going to bounce up and down now if I pull this down an extra X, because it's going to, it's going to pull it back up, and then it's going to, go beyond equilibrium, which means then it's going to drop it back down to here, and then it's going to pull it back up. So what you're going to see is you're going to see this mass, pull this this weight up and down, forever and ever and ever, unless there's something, else acting on it, as like friction or something. So right now we're just going to kind of assume none of those friction forces. It's just going to bounce back up and down indefinitely. So, what we know is the restoring force of the spring is going to be equal to that spring constant times whatever the elongation is, beyond, the unstretched spring. So really what we have is, this was S, which had already pulled down, and then, now let's actually put this back here. So what we know is, without elongation, this is s, and if I pull it down x, this now new spot is going to be s plus x, or x plus s. So what's now going to happen is that spring constant is now going to pull, proportionally to, its stretch. So k times, x plus s. So now we can kind of set up a formula here. What we know is that that our mass times, our acceleration due to gravity, or the acceleration of the mass, is of, our mass is going to be equal to our restoring force plus, mass times our gravity, or acceleration due to gravity. So our mass being, m, our acceleration of the mass is going to be equal to the second derivative of, well, x. Remember that we're pulling this thing down. The x, this is, its position, so it's going to be the second derivative of position. So this is going to be d2x dt2, so the second derivative of that elongation, and this is going to be equal to the restoring force, which is given by, that. So this is going to be equal to minus k times x plus s plus mg. Restoring force means pull it back. Now, when we multiply this other side out, what we're going to have is this going to be minus ks kx minus ks plus mg. And what we know is that this piece right here, this is the same thing as mg minus ks. So this is, our minus ks plus mg minus ks. All I'm doing is just reordering those. And what we know is that that piece is equal to 0, so this is 0. So what we get is m times the second derivative of x with respect to t is going to be equal to minus k times x. Which really is, this is the differential equation that we're actually trying to solve. Here. So if we want to put this we'll mess with this form right here. So let's kind of identify what this thing is. So when I send that kx to the other side, we're going to get this second order linear differential equation, and I can put this in the form that we'd like, which means turn the coefficient of this second derivative as 1, so then plus k over m times x is equal to 0. So then we give some notation on this. So what we're going to do is we're going to let omega squared equal to k over m. So this is going to become the second derivative of x with respect to t plus omega squared x is equal to 0. So that's going to be our notation for this differential equation. Now we're going to have some initial conditions. So what is the position at time 0? And this is going to give us x naught. So this is this means at t equals 0, this is the distance the mass is from equilibrium. And then also sometimes we can apply like a initial velocity to this mass. So if I pull the mass down, and if I just let it go, and what that would be is the initial velocity would just be equal to 0. So if you just pull it down and let it go, the initial velocity is going to be equal to 0. But what happens if I pull it down and then I kind of throw it back up, if I kind of give it a little bit of help? So in that case, I can induce some velocity going, back, and that would be, you know, some number, say x1, and this is at you know, t is equal to 0. This would be the velocity of the mass. You know, at t equals. So it's kind of your choice on how you want to write this. Other ways you can write this is, you know, the second derivative of x plus omega squared times the first derivative of x is equal to 0, and we can solve it that way as well. And if we, you know, have this, what happens is, if I want to solve this differential equation, what we know is we can turn this into r squared plus omega squared is equal to 0. This is, you know, the auxiliary equation, or the characteristic equation. As shown for, you know, solving anything of really kind of like a polynomial form. So then this is going to give us r squared is equal to negative omega squared. So then that means r is going to be equal to, you know, plus or minus the square root of negative omega squared, which is going to give us 0 plus or minus, you know, omega I as far as our answers. We're going to get complex roots here because this is a sum of squares as opposed to maybe a difference of squares. So that means I is going to come in here. And this is only going to be not just complex, but really only imaginary. So that means our solution to this differential equation, you know, our x solution is going to be equal to, you know, some c1, my bad, we should write this as e to the, we said alpha I times c1 cosine of beta t plus c2 sine of beta t. Now, so this would be our general solution for things that have complex solutions, but what we know is that alpha is equal to 0 and beta is equal to omega. So if this is equal to 0, then that term is just equal to 1. So what we're going to get is we're going to get c1 cosine of omega t plus c2 sine of omega t. And it's kind of our choice in the way we want to write our c1s and c2s. If you want to do sine first and cosine second, we just have to be careful of, you know what comes first for sine and cosine. When we do the auxiliary equation for this, sometimes we like to write this as a single trig function. So a lot of times we'll put the c1 in front of the sine instead, and the c2 in front of the cosine instead. And we'll get there after our next example. So a lot of times in the books they might ask you for the period or the frequency given the solution. So say we found our solution, we found our C1 and our C2 and also our omegas, and it asks us to find the period for this motion. So what we know is that the period of a trig function is going to be 2 pi over the coefficient in front of t, so 2 pi over omega, which is going to be 3, and then the frequency is going to be the reciprocal of the period. So in this case, what I know is the period in this is going to be equal to 2 pi over omega, so this is going to be 2 pi over 3 pi. So the period is going to be 2/3, which means the frequency is going to be its reciprocal, which is going to be equal to 3/2. So this is 2/3 seconds, and then its frequency is going to be equal to 3/2. And what this really means is this would be cycles per second. So how many times it goes completely, one full cycle. So it does this 3/2 cycles per second. There's an there's another way of writing this. Instead of writing, say, this in terms of just sines and cosines, what I can do is I can write this in terms of singular, just a sine. So I can say x of t is going to be equal to a sine of omega t plus plus phi. And the way this is actually found is, we'll just say first quadrant right now. So this will be your C1, which in this case is going to go in front of the sine because it's the opposite. And this will be C2, which will go in front of the cosine. And this is going to be equal to phi right here. Now, what we know is that the hypotenuse, A, is going to be, this would be equal to A. This would be the square root of C1 squared plus C2 squared. And then phi is going to be equal to, well, the tangent of phi is going to be equal to opposite over hypotenuse. So then phi is going to be the tangent inverse of this thing. So if I want to rewrite this in terms of just, just the sine function at a phase shift, we know that A is going to be equal to the square root of, well, C1 is going to go in front of x, so minus 4 squared plus 2 squared. So 16 plus 4, so this is going to be root 20. And then I know that the tangent of phi is going to be equal to, we should draw this in its correct quadrant so we can see. So I know that the sine is negative, so this is going to be minus 4, and I'm saying the coefficients, and this is going to be equal to 2. So this is minus 4, this is 2. So when we're looking at our angle here, we know that we're talking about a quadrant 4 angle, so I'm going to use... I have to be careful because when you use the tangent inverse in your calculator, it's only going to give you in the first quadrant. So we need to make sure that we write this in the correct angle. So the first quadrant, it would give us as this, 4, and this would give this as 2. So if I get this angle here, I know this is going to be the opposite of that particular angle. Okay, so this is going to be equal to minus 4 over 2. So theta is going to be equal to... Actually, I could just do it that way. I could just do the positive version and then flip it. Yeah, I'm good with that. Let's just do that. We'll just do this and flip its angle. So then this is going to be the tangent inverse of 4 of 2, which is going to be equal to 2. And what we have is second tangent inverse of 2 gives us 1.1. That's in radians. Let's put it in degrees. Most people like to see the angle in degrees, so they have a better idea what that is. So about 63.4 degrees. It's about 63.4 degrees. So what I can rewrite the solution is x of t is going to be a, which is the square root of 20, or 4 times 5, or so 2 root 5. And this is going to be sine of omega. Omega is still that 3 pi t. And this is going to be minus 63.4 degrees because it's down here in the negative. So sine of 3 pi t minus 63.4 degrees. Okay, so finally we get to solve a spring constant. Now that I know basically all the things, let's do an example for undamped motion. So mass weighing 2 pounds stretches the spring 6 inches. At t equals 0, the mass is released at a point 8 inches below the equilibrium with an upward velocity of 4 feet per second. Determine the equation of motion. Now, let's get to this this velocity, because this is something that we tend to have to pay attention to. So when we're pulling things down, we'd say the acceleration due to gravity is, in feet, is going to be 32, feet per second. But we know that it actually pulls it down. So we have a choice here, do you want 32 to be negative? So do we want this to be a negative number? Or do you want, up to be a negative number? So it's kind of our choice as far as our coordinate system. Now, in general, we tend to, let the acceleration due to gravity be the positive thing. So really positive means this way. And since this is going to be going with an upward velocity, I know that upward is going to be opposite of what the gravity is going to be. So if I choose the gravity to be positive, then this number is going to have to be negative because it's going the opposite direction of gravity. So that's kind of the disclaimer. Be careful. A lot of times we choose this way to be positive when we're doing these particular examples. All right, so let's get started. So first things first, since we're using gravity as 32 feet per second, and a lot of times our weights are going to be in pounds, we need to turn all our inches into feet. And you can also see that this is feet as well. So what we know is that 6 inches is equal to a half of a foot, and 8 inches is going to be, also another way you can say that this is 6 over 12. That's why this is, 6 inches is 6 of 12. inches, which is why it's half of a foot, so it's going to do that. So this is, 6 inches divided by 12 inches. That's why this is, equal to 1/2 of a foot. Now, very similarly, we can say that 8 inches is 2/3 of a foot, so 8 inches. I don't like the way I did that. I hate the way I did that, actually. So if I have my 6 inches, I'm going to multiply that. It says 1 foot is equal to 12 inches. I like that much better. So that's why this is equal to, 1/2 of a foot. And very similar, if I say 8 inches, we can take our 8 inches and then we can multiply it by a unit factor that says 1 foot is equal to 12 inches. So that's why 8 over 12 is going to be equal to 2/3 of a foot. That's much better. Okay. Now, we know that W is equal to M times G. So, our weight was equal to 2, and our force of gravity is equal to 32. So, our goal is to be able to find M, because in order to find omega, what I'm going to need is I'm going to need to know M and the spring constant. So our goal is to be able to find this M, and all I've been given is this particular weight. So so in this case, that 2 is equal to M times the force of gravity, which is going to be 32. Now we got to remember I'm making this positive, that's why it's 32. So then that means that M is going to be equal to 2 over 32. Which you'd say 1 over 16. And when we're using, feet, seconds, and masses, this units is called slugs. Thank you, English system. Okay. So, Hooke's law, we'll get there eventually. Hooke's law now says F is equal to K times S. So, our weight being equal to 2, and this is going to be K times our elongation, which was 1/2 of a foot. So that means K is equal to 4. Ooh, that's a lot of work. So, okay. Well, again, what our goal was to do is we tend to use these two equations, so then we can find our K and our M, and then we can determine what omega is, because omega happens to be part of our solution for our differential equation. So finally, omega squared, which we know is K over M, is going to be equal to K is 4, M is 2 over 32. So this is going to give us 4 over 1 multiplied by the reciprocal of 32 over 2. So this is going to twice. So that means this omega squared is going to be equal to 64. So finally, our differential equation. So what we know is that the second derivative of x with respect to time plus omega squared times x is equal to 0. And what we know is omega squared is equal to 64. So if you prefer this, second derivative plus 64 first derivative is equal to 0. We know that we're going to get solution to this using the auxiliary equation, the characteristic equation of 0 plus or minus 8i. So that omega, which is equal to 8, really is going to be what goes in front of our solution. So, it has only imaginary parts, so this is going to be, C1 sine of omega t plus C2 cosine of omega t, where omega is going to be this, the solution of this, which is 8. So this is going to be equal to C1 sine 8t plus C2 cosine of 8t. So that is our solutions, which is neat. So really, once you know omega squared, you don't even really have to write the differential equation. You know how to solve these second order linear differential equations that happen to have complex roots. Boom, there it is. And now, how do you find C1 and C2? Well, C1 and C2 come from our initial conditions. So the first initial condition, we know that what was the position at time 0? Well, what it said is the mass was released at a point 8 inches below the equilibrium. Remember, down being positive right now, 8 inches below is going to be equal to this 2/3. So this is equal to 2/3. And then our second condition, let's write this k equal 4 here. Our second condition says that the first derivative of x, which was this initial upward velocity, and this is going to be, in the correct units is right here already. So this is minus 4/3. Remember that it's being pushed up, and if I'm calling this positive, that means this way is negative. So I guess we have to find the derivative of this thing. So x prime of t is going to be equal to c1 cosine of 8t minus c times 8. And this is minus sine of 8t times 8, so this is minus 8c2 sine of 8t. So now plugging 2/3 into here to find c1 and c2, and then negative 4/3 into here to find c1 and c2. We'll solve this system of equations. So c1 sine of 8 times 0 plus c2 cosine of 8 times 0 is equal to 2/3. And then similar over here, we have 8c1 cosine of 8 times 0 minus 8c2 sine of 8 times 0 is equal to minus 4/3. Now the sine of 0 is 0, so that's gone. So this whole thing is gone. And the cosine of 0 is equal to 1, so this says c2 is equal to 2/3. And similarly, the sine of 0 is equal to 0, so this entire term is gone. And the cosine of 0 is equal to 1, so this says 8c1 is equal to minus 4/3. Divided both by 8, so this is minus 4/3 times 1/8. So 4 goes into that twice, so this is going to be equal to negative 1/6. So finally, our solution, given the initial conditions, comes from here, where c1 is going to be equal to minus 1/6 sine of omega, which was 8t, and then plus 2/3 cosine of 8t. If you want this in the other single solution where it's just sine, we know that a is going to be the square root of c1 squared plus c2 squared, so 1/6 squared plus 2/3 squared. So this is going to be the square root of 1/36 plus 4/9, so divided by 4, so this is going to be the square root of 17, that'd be 16 plus 1, all over 36, where 36 is 6, that's our A. And then we also know that the tangent of phi is going to be equal to c1 over c2, c1 going to be this minus 1/6, c2 is going to be equal to this 2/3, or 4/6, so this is going to be minus 1/4. So very similar. If I want to take the, we'll take the tangent inverse of 1/4 and then make its angle negative. So second tangent inverse of 1 divided by 4 gives us 14. So it's going to be, that'd be 14 degrees if it was positive, but it's in quadrant 4 because, again, the sign is negative, so the opposite is negative. So phi is going to be about negative 14 degrees. So therefore, x of t is going to be equal to root 17/6 sine of omega t minus 14 degrees. Or if you want this in radians, second, we have about, if you want this in radians, we could write this as 0.245 radians. So if you like the content, please subscribe.